Hi, this lesson is about related rates word problems. So with related rates word problems, you're going to calculate the rate of change of one variable or quantity in terms of the rate of change of another. And usually you're calculating these rates of change with respect to time. In fact, all of the ones that we'll be doing today will be changing with respect to time. So some of the steps you're going to want to consider, probably in the order I have listed here with the bullet points, is first you want to identify the formula that's related to the problem. Sometimes it will be obvious, it'll be a geometric shape, or other times you'll need to draw a picture. Oftentimes you'll be using pictures associated with triangles, so that might be like the Pythagorean Theorem is often used with these problems. You want to identify which parts of the formulas are changing and which parts are constant. This is really important. So anything that's constant, you're going to want to substitute into the formula that you identified in the first step before you take the derivative. If necessary, you may need to make substitutions of one variable in terms of another, and that information will be in the problem. Sometimes, for example, there's a relationship between the height of a cylinder and possibly its diameter or its radius, for example. Then you want to take the derivative of both sides of the formula implicitly, which means that you're going to be following your derivatives by the derivative with respect to time. So if you're taking the derivative of a area of a circle and both the area and the radius are changing, then when you take the derivative of area, that'll be a dA dt. But when you take the derivative of the radius, you're going to follow that derivative by dr dt. So you'll see examples of this soon. And in the end, once you solve for the related rate that you're looking for, remember to include the appropriate units. So here are a few examples. So example number 1. If V is the volume of a cube with an edge of length x, and the cube expands as time passes, find dV dt in terms of dx dt. So first thing you need is the formula. Well, the formula for the volume of a cube with an edge of length x is V is equal to x cubed. So if this cube is expanding, both the volume and the edge are changing. Therefore, the derivative of volume is dV dt. The derivative of the right side is 3x squared, that's your power rule, followed by the derivative of x, which is dx dt. So the formula that we were asked for is to find dV dt in terms of dx dt. That's what you see right here in the pink box. All right, next example. It's telling you if y is equal to x cubed plus 2x and dx dt is equal to 5, find dy dt when x is equal to 2. So the wording of the question is telling you that both x and y are changing with respect to time. So first thing we need to do is take the derivative of both sides. The derivative of y is dy dt. The derivative of x cubed is 3x squared followed by dx dt, and the derivative of 2x is 2 dx dt. Well, now we're ready to plug in the numbers that we know. Remember, we're solving for the value of dy dt. So we plug in x equal to 2, that's given, and we plug in dx dt equal to 5 right in here. Okay, so we get 3 times 2 squared times 5 plus 2 times 5. Then when we make the calculation, we have 60 plus 10, so our dy dt has a value of 70. Okay, let's move on to number 3. Number 3 says that each side of a square is increasing at a rate of 6 centimeters per second. At what rate is the area of the square increasing when the area of the square is 16 centimeters squared? All right, so again, we need a formula. The formula for the area of a square, I'm going to call the side S, is A is equal to S squared. So it's asking us to find the rate of change of the area. It says, what rate is the area of the square increasing. So any kind of change, increasing, decreasing, words like that are important. Expanding, shrinking, um, melting. Those are all words that represent some sort of change in something. So here we take the derivative of both sides. I have dA dt equals 2s ds dt. Because remember, if the square is increasing, both the area and the side are changing. Now we need to plug in numbers. Now to plug in numbers, I was told that that the side is increasing at 6 centimeters per second. Well, that's ds dt. If your side is changing per some unit of time, ds dt is 6 centimeters per second. Then you're also told that your area is 16. That was given in the problem. But I don't really need to know that the area is 16. I need to know what the value of s is. So if you take the square root of both sides, when the area is 16, the side must have a length of 4 centimeters. So now that I have all the information I need, I'm ready to plug it in right here. So I have 2 times s, which is 4, times ds dt, which is 6, and that works out to be 48, and the units are centimeters squared per second. All right, so let's move on. It says air is pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. So whenever you see something like this, 100 centimeters cubed per second, something changing with respect to time, that tells you it's a derivative. And because I'm talking about centimeters cubed, it's going to be some derivative with respect to volume. And the question is, how fast is the radius of the balloon increasing when the diameter is 50 centimeters? And here you're told that the volume is 4/3 pi r cubed. It's probably a formula that you should know that would help you in calculus course, physics courses. So you should probably memorize that the volume of a sphere is 4/3 pi r cubed. All right, so first we have to figure out what they're asking for. They're asking you to find how fast is the radius changing when the volume is changing at 100 centimeters cubed per second. So we want to find dr dt when dv dt is 100 and your diameter is 50. If your diameter is 50, remember the formula doesn't have diameter in it, but it does have radius. When the diameter is 50, your radius is 25, because twice the radius is the diameter. Okay, so now we take our volume formula. So I'm right here right now. And I take the derivative of both sides. The derivative of v is dv dt. The derivative of 4/3 pi r cubed, you have to apply the power rule. So it's 4/3 times 3 pi r squared followed by dr dt. Well, the 3's will cancel. So on this last line here, I have that dv dt is equal to 4 pi r squared dr dt. So now we're ready to substitute what we are given and solve for dr dt. So here, dv dt is 100, so we have 100 is equal to 4 pi, and the radius is 25, so it's 4 pi 25 squared dr dt. You want to divide both sides by 4 pi 25 squared, and then simplify. It's probably easier to simplify than to square the 25. 4 goes into 125 times, which is why I have a 25 in the numerator. So now I have 25 over pi 25 squared, and then the 25 in the numerator cancels with 1 in the denominator, and your final answer is that dr dt is changing at 1 over 25 pi centimeters per second. All right, here's another one. It says a ladder that is 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall. Okay, so we have to set up an equation. It's asking us to find dy dt when dx dt is 1 foot per second. Now, that comes from the picture I drew here. You really could use any variables you want. If I'm calling the vertical side of the wall y and the horizontal side x, it's asking how fast is the top of the ladder sliding? Well, that's dy dt. And it says that the bottom of the ladder is sliding at a rate of 1 foot per second. Well, that's dx dt. And we want to know what's dy dt exactly when the ladder is exactly 6 feet away from the wall. So that's when x is equal to 6. So you can see from the picture that I'm going to use the Pythagorean theorem. So I have here, the Pythagorean theorem states that x squared plus y squared equals 10 squared. Now, it's okay for me to plug in 10 right away before I take the derivative because the length of the ladder is not changing as the ladder slides. Only the x value and the y value will change as the ladder slides. So that's an example of where you want to substitute in the constant before taking the derivative. So now we're on this line. We're taking the derivative of both sides. The derivative of x squared is 2x dx dt. The derivative of y squared is 2y dy dt. And the derivative of 10 squared or 100 is 0. All right, so now we're ready to plug in what we know. Remember, you were told that dx dt is 1 and x is 6. But I don't know what y is. So in order to figure out what y is, I have to come here to this work right here. And I'm going to use the Pythagorean theorem to figure out what would the value of y be, or the length of the vertical side of the triangle be, when my x is 6 and my ladder, or my hypotenuse, is 10. So 6 squared plus y squared equals 10 squared. So 36 plus y squared equals 100. Subtract 36 from both sides. You get that y squared is 64. And so y is equal to 8. So we don't have to consider plus or minus 8 because 8 is the length of the wall. You wouldn't have a negative length or a negative dimension when you're talking about a triangle. So now all that information gets plugged in right here. The x, the y, and the dx dt. So I have 12 plus 16 dy dt equals 0. Subtract 12 from both sides, and then divide by 16. And then when you reduce negative 12 over 16, you get that dy dt is equal to negative 3/4 foot per second. And it's negative because the ladder is sliding down the wall. Okay, so now we move on to number 6. Number 6 says a cylindrical tank with a radius of 5 meters is being filled with water at a rate of 3 meters cubed per minute. How fast is the height of the water rising? So again, I gave you the formula. So the formula for a cylinder is V is equal to pi r squared h. That's also a good one to know. You should know the formula for the volume of a cylinder. So the question, if I translate the words into math notation, is asking you to find dh dt, right? That refers back to how fast is the height of the water rising. Rising indicates a change. When dv dt is 3 meters cubed per minute. And again, the unit of measure gives it away as a derivative. This is a derivative of of v. So dv dt is 3 meters cubed per minute, and you're told that the radius is 5. So let me remind you that a tank looks like this. And remember, it's as water is filling it. So here's my height. Here's my radius. As water is filling this tank, both the volume and the height are changing, but the radius is a constant. This is a constant value. So again, like the last example, any constant value you're going to want to substitute it into the formula. So here's our formula right here. V is equal to pi r squared h. But don't take the derivative yet. First substitute 5 in for r. So v is equal to pi 5 squared h, which is v is equal to 25 pi h. Now we're ready to take the derivative of both sides. The derivative of v is dv dt. The derivative of 25 pi h, remember 25 pi is the coefficient of h. So the derivative on the right side is 25 pi dh dt. So now we're ready to plug in what we know and solve for what we're looking for. So right here, we replace dv dt with 3. 25 pi dh dt is on the right. Divide both sides by 25 pi, and you get that dh dt is 3 over 25 pi meters per minute. Okay, here's another one. Gravel is being dumped from a conveyor belt at a rate of 30 feet cubed per minute. So hopefully by now you realize that this represents a derivative, and this will be a dv dt. Unit of measure gives it away because of the feet cubed. And the coarseness is such that it forms a pile in the shape of a cone whose base diameter and height are always equal. That statement is important. How fast is the height of the pile increasing when the pile is 10 feet high? So this statement right here tells you what you're looking for. We want to find dh dt when your h is 10. Okay, so let's translate what it is we need to solve for in terms of what we know and the variables we should be using. We want to find dh dt when dv dt is 30 feet cubed per minute and h is 10 feet. You're also told that the diameter and the height are always equal as this gravel is poured onto the ground. But again, our formula does not have a diameter in it. It has a radius. And so diameter is 2 times r. And if I solve for r, I get that r is equal to h over 2. Now, the reason why we want to do that is because we're going to want to use that information, this r equal to h over 2, to substitute it back into the formula. And the reason for that is because I don't know how fast the radius is changing with respect to time. But I do know how fast the volume is changing, and I do know that I'm looking for how fast the height is changing. So we need to eliminate r from our formula so that we can solve for what we're looking for. So here, if I return to what the formula is, I have v is equal to 1/3 pi r squared h. Then we substitute r, which is h over 2, in here in the formula. So v is equal to 1/3 pi h over 2 squared times h. And then we move on because now we just want to simplify and combine the h's as well as our coefficients. So I have 1/3 pi h squared over 4 times h. The 1/3 and the 4 in the denominator becomes 1/12 pi, and h squared times h becomes h cubed. All right, so now we're ready to take the derivative of both sides of the equation. Volume and height are changing as gravel is being dumped. So the derivative of v is dv dt. The derivative on the right, you have to use power rule, so it's 3 times 1/12 times pi, so that's 3/12 pi. Subtract 1 from the exponent, so we get h squared, followed by dh dt. So now we're ready to substitute in what we know. So I'm right here. So dv dt is 30. The right side, the 3/12 becomes a 1/4 pi. H is 10, that's given in the problem, so it's 10 squared dh dt. All right, so next line right here is I have to square the 100. So I get 30 is equal to 1/4 pi 100 dh dt. But 1/4 times 100 becomes 25 pi dh dt. Then we have to divide both sides by 25 pi in order to solve for dh dt. So dh dt is equal to 30 over 25 pi, but 30 and 25 have a common factor of 5. If you divide them both by 5, you get that dH dt is equal to 6 over 5 pi feet per minute. Okay, so there's one more. We have a plane flying horizontally at an altitude of 1 mile and at a speed of 500 miles per hour passes directly over a radar station. Find the rate of the distance from the plane to the station. Find the rate that the distance from the plane to the station is increasing when it is exactly 2 miles away from the station. Okay, so the 1 mile is the height right here. So here's the radar station. The plane is above it, 1 mile above it, and it's flying. It's flying away from the radar station. It's going in that direction. And we know that that plane is traveling at 500 miles per hour. And we want to know how fast the distance from the radar station to the plane is increasing. So if we were to translate, again, the words using the picture and the variables that I'm using, that means I want to find dz dt when z is exactly 2 miles. And given that dx dt is 500 miles per hour. Remember, that's how fast the plane is moving. So again, we use the Pythagorean Theorem. So I have x squared plus 1 squared equals z squared. We replace the 1 because the height or the altitude is a constant. So now I can take the derivative on both sides. So I'm right here. I have 2x dx dt plus 0 equals 2z dz dt. All right, so I can plug in what I know. I know dx dt and I know z, but I do not know x. So to figure out what x is, I go back to the Pythagorean theorem. So I'm right here. I have x squared plus 1 squared equals 2 squared. The 2 was given in the problem, 2 miles away, when the plane and the radar station are 2 miles away. So we have x squared plus 1 equals 4. Subtract 1 from both sides, you get that x squared equals 3. Take the square root of both sides, you get that x is equal to the square root of 3. Remember, that's a distance. So we do not want a negative number there. X is root 3. So now I can plug in to my equation and solve for the unknown. So I have 2 times root 3 times 500 equals 2 times 2 dz dt. On the left side, 2 times 500 becomes 1,000, so I'm right here. And then I also have to divide by 4 because of the coefficient here. So I have 1,000 root 3 over 4. And when you simplify that, you get 250 root 3. And here the units are miles per hour. So now you should try 14.1 homework.